be presenting and trying to give you a kind of general overview, jumping again into a different topic compared to everything that was before. So it's a kind of wide bandwidth session, I would say, from this perspective. So this is the short outline. So generally, the vision would be that we see the future of MEMS-based microsystems in a combination of MEMS plus digital electronics. Sigma delta is already there. Then why do we need sliding mode control? And we'll discuss about the sliding mode control applied for normal MEMS accelerometers, and even more interesting, for stabilizing actually accelerometers operating on the border of their stability, because that's the interesting part. So the present status in inertial MEMS sensors. We know already that for high sensitivity, we do need a closed loop operation, yeah, just in order to keep the disturbances away, just in order actually to get that high performance with a bandwidth compromise, we do need the closed loop. So as I said, within the closed loop, taking into account that the interaction, the electromechanical interactions with our inertial sensors, in this case with accelerometers, is of nonlinear nature, we see more and more the digital electronics actually pouring and taking place of replacing completely actually the analog functionality from this perspective. And this happens either if it comes to inertial navigation, where we need actually relatively high sensitivities, or even more advanced explorations like oil exploration in this case. Obviously, in this case, the level of noise that needs to be achieved is even at a much lower values. So, from this perspective, I would say that we move gradually toward a kind of digital era. We are not limited in the computational power, we are rather limited in the power of processing in the analog domain nonlinear signals. So, the general vision, pervasive so now, is that MEMS, we try to surround the sensor itself, either that is an accelerometer or a gyroscope like in this example. We try to surround it with a thin analog layer, and after that the general control loop is providing all the entire computation within the digital system. So ideally we would like to have this type of bidirectional interface in the digital domain, digital actuation, digital sensing. And the classic approach is a sigma delta force feedback. An example is here for a gyroscope having a bandpass sigma delta actually for the driving mode, and a normal sigma delta actually, a low pass sigma delta for the sensing mode in this case. So, just to perhaps clarify a bit, or present a kind of sigma delta approach in the nutshell, because this is the state of the art we want to compare with. It's a technique that was coming into the MEMS world from the ADC part, from the electronic design. And already the complexity was shifted from the analog to the digital domain, because we need only a very simple ADC, but then we have a more complex digital signal processing. So there are a couple of key concepts: oversampling, noise shaping, digital filtering, and decimation, and all come into pieces when they are integrated into the sigma delta applied to MEMS world, yeah? So the oversampling firstly reduces, the concept is clear, yeah? It spreads the noise into the bandwidth. Then by doing the digital filtering, you can eliminate part of that quantization or other type of noise that appears into the system. Is it enough? Not necessarily. Basically, every factor of 4 in oversampling gets you one more bit. So it's necessary to add to this a shaped noise, to shape the noise of the system by adding the integrator, and that was actually what brought the entire field of sigma delta applied to accelerometers in this case, because instead of that integrator, you will have the equivalent transfer function of an accelerometer, which is equivalent with a second order system. So you will get basically a second order sigma delta if you don't have any other higher order integrators or other parts modifying the transfer function. So it looks okay from this perspective. Now let's go to, let's say, what is wrong? What are the limitations actually in the present sigma delta approach? So if I imagine putting a generic MEMS sensor and controlling it to a sigma delta from a sigma delta perspective. So I will have the sensor put instead of the integrator there, and it will create by itself, in the case of a MEMS accelerometer, you'll already generate a second order system. Everything is good up to the point where trying to push it toward higher order sigma delta architecture. So the state of the art these days are typically the fifth order sigma delta architectures, but then the stability becomes a serious concern, and you need a lot of effort actually to start pushing beyond and to start actually tuning. Why? Because the theoretical framework, the entire design methodology applies, I would say, linear design techniques. We are electrical engineers. Whatever we see in the circuits, we want to reduce to Ohm's law. It's the same here. Whatever we see in the systems, we try typically to treat with a linear transfer function into the frequency domain, and as a result, this is an essentially nonlinear electromechanical coupling, but we try to split it into a linearized transfer function for the signal, a linearized transfer function for the noise, and then to put them together and to solve and to try to optimize the system. Is there another way? Well, sliding mode control has been present for a while. It is called also variable structure control. It has been present into the mechanical domain. It has a relatively rich theoretical framework based on discontinuous feedback. It's actually the idea of differential equations with discontinuous right terms. And it has a robust and simple implementation. It has also, what is very interesting from the perspective of the present talk, the possibility of stabilizing unstable nonlinear systems. So while in the case of sigma delta, I have a problem actually keeping the stability itself in the closed loop, in this case, I can imagine actually pushing the system to the border of stability, and through the sliding mode control, I can stabilize it. So, to discuss about the concrete cases that we have had in our lab, we have a set of several accelerometers, all of them designed in SOI month process, so I will not enter too much into details, except the fact that we designed them in such a way that we have different ways of coupling and sensing. Yeah? So we have, in some cases, we have accelerometer for which we have both area varying capacitors and gap varying capacitors to be possible to interface neatly for all the simulations and experiments that we have done. So, from the perspective of the basic methodology in the sliding mode control, you regard the design in the state space, and you have two steps in the control. The first one, you try to ensure the so-called convergence of the trajectory to a sliding surface. That is nothing else than actually a reduced dimension surface actually into the state space. If I have my state space defined by x and y, x and displacement and velocity, then it will be just a relation between those two, a curve. And then in the second phase, you try to maintain the trajectory on the sliding manifold to a fast switching action. So this will be the example of the proof mass. I'm interested only in the digital actuation in order to use the complete similarity with the sigma delta case. So in other words, if I'm on the right, I will apply a negative force. In other words, I will apply a fixed level of voltage that maps to a force that restores it in the opposite direction, and it will be the other way around if the proof mass moves to the left. This is in the case of defining the reference position at 0. So that will be the proof mass, and now let's see a bit the state space view. That's the general idea. You see the red line, it defines actually the so-called sliding mode surface. It's basically ensuring that whatever trajectory I have in the state space, it will converge firstly into the first steps. There will be a transient converging toward, let's say, the black one is here, yeah? So it will converge toward the sliding mode surface, and then it will start actually switching back and forth actually along that line, converging toward the equilibrium position. Now, the controller obviously is binary, as I said. You can define this equilibrium position not only at 0. That's the interesting part. So you can actually define in a generic case a desired position that, as I said, you could put it, you can set it into the unstable region, in fact, at pull-in, which will correspond roughly to a distance that is larger than 1/3 of the gap at that point. So you can move in that area and still use the same approach for implementation. What will be the advantage? The advantage will be that it's a digital implementation. It's much simpler to map it to FPGA, for instance, than a sigma delta, and it can, as I said, stabilize the accelerometer into a kind of highly sensitive area. So the sliding surface is defined by this error, sliding mode surface keep to 0. In the first phase, you have the convergence of the dynamics to the sliding surface, and then, because you discuss, let's say, I don't enter into the mathematical details, but you can ensure a convergence by minimizing or ensuring that the error energy is actually negative, the derivative of the error. So once the trajectory is on that sliding surface, the net action will be given by a so-called equivalent control variation. If I put them together, the key part that differs from what is presented in mechanical engineering at sliding mode control, where they say that chattering that happens along the sliding surface is something very negative and you need to get rid of it. In reality, you can take it into an advantage, turn it into an advantage by recovering, actually by low-pass filtering, recovering the input acceleration out of that filtering. It's the same way like in sigma delta, actually, you low-pass filter actually the bitstream to recover the external acceleration. The same principle applies here. And this is an example, for instance, of a sliding mode with in the case of those accelerometers with a reference signal set to 0. In other words, I balance actually the accelerometer on the equilibrium position, and I have an input acceleration, and you see on the right side, if my mouse obeys me, you see that the system works actually for both underdamped accelerometers and overdamped accelerometers. So you have the possibility. It's a relatively robust system implemented on FPGA. And what is more interesting is what happens if I push it on beyond the stability border, I would say. I push it into the pull-in region, actually. Because the recipe generally for getting very high sensitivity in such kind of sensors is, on one side, I mentioned to operate in a closed loop. Secondly, it's better if I put an operation in the closed loop, but within a region of very high sensitivity, in such a way that I want to position it on the stability border, so I apply a voltage that is slightly above actually the pull-in on a separate pair of COM drives, and then I use another pair of COM drives actually to operate in a closed loop and to maintain the system. So the readout is relatively simple. It's made at the PCB level, in fact. So it relies just on some fully differential capacitive readout system. So I suppose there is not too much time, so and I will skip over this part. And I present actually the experimental setup. So you have the MEMS accelerometer, you have the analog PCB, and then the entire digital electronics is implemented into a Virtex FPGA system. In reality, we have cheated a bit because we have used LabVIEW FPGA module in order to make it easy, to not dig too far into the VHDL code. So you have an image of the setup, and here is an example of the stabilization beyond the pull-in of the system. So we manage actually to stabilize the position of the accelerometer into a very high sensitive area. And if it is to compare, so that will be the transition curve when I apply a variation, a step function that is slightly higher than the pull-in. Yeah? Typically, the blue line will be the transition toward pull-in, going through a kind of metastable region. The red one will stabilize actually the system. And these are the results responding to the step function, or even more interesting, for exactly the same accelerometer with a normal operation, taking as a reference point the balance at 0, we get responses in the order of hundreds of milli-Gs that we can measure. In the moment in which we start biasing into the pull-in, we already can increase actually the sensitivity by order of magnitude by just the simple operation. Again, I need to emphasize on the fact that it is exactly the same device, the same MEMS structure. I don't vary and I don't use another one. So, conclusions. It's a good digital system alternative to a sigma delta because it allows us from the beginning to embed the nonlinearity into a kind of theoretical framework. It is also, it offers a simple FPGA implementation, and it offers you the possibility to stabilize it on the pull-in border. With this, I will stop. Thank you.
Thank you very much.